Welcome to Chemistry 112. Today we will first work on some electrochemistry homework, which is the last major assessment due. There will still be a learning curve over the next chapter, but there will not be like an actual homework assignment. It will not be a 50-point assignment, just a shorter 25. So for chapter 20. So we are almost, while the homework is not due for a while, all the stuff is not due for a while, we are almost at the very end of the material. Almost at the very end of the material. Maybe we're going a little bit faster than maybe we need to, but than originally had planned, but we can slow down a bit once we get through it, do some review, understand this, practice some test stuff before we have the actual test. Don't forget, for people in lab, that turn in your assignments. If you have a question of what you need to turn in, let me know. I'll look it up and I'll be able to get back with you. Don't forget to do the online labs. Yes, you could possibly work together with your partner, make it a little bit easier on everyone. 3 online labs by the end of the semester. So don't forget to get those done. So we're going to start with electrochemistry and then maybe start into nuclear chemistry. The nuclear maybe like the first half of the nuclear chemistry stuff will be on the test, but I promise it's not going to be too tricky. And that part of it deals with atomic structure and counting the atomic mass and the atomic number, and the other part will be kinetics again, and specifically first order kinetics. So we've done that, so it's just a repeat of that, maybe a little bit easier. Now, to get started, I'm going to plug in my document camera. Okay, we kind of started looking through some of this on the on last class, but we didn't get very far. So we'll continue with this. There's 20 questions, but some of these are actually really easy, like determine the oxidation state. I'm not going to run through all of these because some of these are kind of no duh. If it's, for example, like if it's a pure element, it's a pure element in its standard state, and it's chargeless, it is considered oxidation state 0. So when it says Ag solid, you can just, oh, that's just 0. When it's an aqueous ion all by itself and it has a charge, the oxidation state is the same as its charge. So don't overcomplicate it. Ag plus is just going to be +1. Copper 2 plus is just going to be 2 plus. The only hard part here is answering the question, which one is oxidized, which one is reduced, and then balancing this. Which one oxidized? Remember, oxidation is loss of electrons. Electrons are negative. Oxidation is the guy who becomes more positive. Reduction is gain of electrons. So which one of these guys goes less positive? Balancing that, I mean, we'll go ahead and balance this real quick. Now, this one's done in basic solution. Phases are optional. So let's write down our 2 half reactions and work from there. We'll write these down, MnO4 minus, and Fe3 and Fe2. Okay. I got this down on my notebook. I can go to the doc cam. It's okay. I'll move that up a little bit. Step 1 is always balance the elements. So manganese, manganese, those are good. Iron, iron. Step 2, balance the oxygens. 4 oxygens, 2 oxygens, 0, 0. So 4 oxygens, 2 oxygens, I have to add 2 waters. Step 3 is balance the hydrogens now. 2 times 2 is 4. I have to add 4 H pluses on the right. So at this point, we need to balance the charge by adding electrons. So the left charge and the right charge have to be the same. The left charge here is 0. The right charge here is -1 plus 4, so positive 3. Positive 3. So what am I going to do? I have to add 3 electrons. Now to this guy, 3 plus 2 plus. How do you get from 3 plus to 2 plus? We're going to add an electron here. So this one is the gain of 1 electron. This guy is the loss of 3 electrons. Now, one other thing. This is asked to be in basic conditions. I can do this at the end. I can do this in the middle. I can do it whenever. But to make this basic, I'm going to add OH to both sides until all the acids are gone. There's 4 acid molecules on the right, so I'm going to add 4 OHs. But to add 4 OHs to one side, I have to add 4 OHs to the other. So this 4 OHs and 4 H's cancels to give you 4 water molecules. And this one is just 4 OHs. Now, 2 water molecules cancel with 2 water molecules. So the new equation here is MnO2 plus 4 OHs gives you MnO4, 1 minus, 2 waters, and still 3 electrons. Now that's 4 negative, 1, 2, 3, 4 negative, still balanced. Another quick rule is that essentially, if you noticed, this was 2 and 4. What is it now? It's 2 and 4. You're just flopping the H's to an OH on the other side, and the water flips side. But now the last step is I got to combine these together. I need 1 electron to cancel out 3 electrons, so I'm going to have to multiply this whole thing by 3 and add them together. So the balanced equation would be some form of MnO2 plus 3 iron, 3 plus, and 4 OHs goes to MnO4, 1 minus, 2 waters, and 3 iron, 2 pluses. You'll notice this is 6 plus, so the net charge is 5 plus on this side. The net charge here, 3 times 3 is 9. 9 minus 4 is 5 plus. The big thing is the charge on both sides must be balanced as well as the elements. But if you follow these rules, you will be fine. For the upcoming test, I'm going to allow you to have that same little stupid notebook sheet. So if you want to show an example of you working in balancing an equation like this, go right ahead. I understand it is not necessarily easy and not something you can perfectly memorize each time. You're sometimes going to forget a step. So don't wait to the last minute. Don't come into the test and be like, oh, I forgot. If you do it now, if you work on it now, when the test comes in like a week or 2, or you will be all ready. So okay. Okay, don't forget, cathode is where the reduction occurs. The anode is where the oxidation occurs. Considering the galvanic cells always occur in spontaneous way, so you always have a positive cell potential, and they should always be written anode to cathode. Anode on the left, cathode on the right. I may have updated some of the notes to reflect that, with some minor errors cropped up. Okay, so galvanic cell where aluminum is reduced to aluminum metal. That is wait. And I think they must be writing the cathode on the left. The cathode to anode. I'll have to look. But so either way, the anode is where the oxidation occurs, and the cathode is where the reduction occurs. So no, it's anode and cathode. Yeah. So in this case, you're just writing what is the half reaction. You're saying at the cathode where the reduction occurs, aluminum 3 plus 3 electrons goes to aluminum solid. Magnesium metal is oxidized to Mg2 plus. You just have to write Mg goes to Mg2 plus and 2 electrons. So pretty straightforward. I'm not even gonna. Now this one, recognizing parts of the electron. So writing this cathode, anode and cathode. There, X is saying X is more reactive than Y. That X more readily reacts to form cation than Y does. So X is going to be oxidized and Y is going to be reduced. So they're trying to tell you that, looking at the diagram on this one, if X is going to X2 plus, the X electrode will then lose mass because it's going to start dissolving. Thus, Y will gain mass. Because it's being oxidized, it is the anode, meaning the other guy is the cathode. The anode is negative, and the cathode is positive, so electrons are going to flee the negative, be repelled by the negative, and go to the positive. So from that, electrons, the wire will flow away from the anode, and electrons will flow towards the cathode. And finally, because this is negative, cations, no, so we have to, in this case, anions will flow towards it, and cations will flow toward that. This is the little contradictory part, because essentially we're building up a 2+ charge in the solution. It's going to keep building up as more dissolves. So in order to keep the solution neutral and thus make the reaction work, negative charges must go to counter the positive. The same way here, as Y2 plus leaves, you're going to build up an absence of charge. It's going to become less positive and thus more negative. So how do we counter that? The cations are going to have to enter solution to replace it. But all that can be gleaned if we go back to the notes and look at some of that. Once again, cell interactive. Do that, you look at that, and it should answer most of these questions. But hypothetically, we don't need the interactive to do it. More of this. Remember, when we write these half reactions, this is just a word version of the diagram of that battery. This is the anode. This is the cathode. This is reading from left to right. Copper goes to copper 2+. Silver goes to silver solid. I'm just reading left to right. This is the molecule is jumping from the single line across the single line. That single line is like an arrow. That double line tells us, oh, that's the separation of those two half reactions. So just looking at this, copper. Oh, come on. Copper, arrow, copper, 2 plus 2E. That's all. I mean, that's essentially all you'd have to do. And then Ag plus electron minus arrow Ag. Especially if it doesn't say anything about including the units or the phases. And then, of course, you just have to balance that together. And that'd be like what? Copper plus 2Ag plus goes to 2Ag and copper 2 plus. Why do you say 2Ag? So the reason I needed 2Ag has to do with there's 2 electrons here and 1 electron here. So to balance this, I have to double this half reaction. So that 2 electrons lost will equal 2 electrons gained. So 2 plus on the left equals 2 plus on the right. And if I get this wrong, the only reason would be due to states of matter. And no, that one clearly doesn't even need the states of matter. So you don't. This one, first time we actually calculate cell voltage. If they say, here's our 2 reduction potentials. And they say standard galvanic cell where X is the anode, Y is the cathode. So it's cathode minus anode. Cathode minus anode, but it's basically the guy who, remember, the guy who gets reduced, minus the guy who gets oxidized. The oxidation is on the left, which is why it's cathode minus anode. But the guy who gets reduced, which is 0.18, minus the guy who gets oxidized, which is negative 2.08. Go into so because this is galvanic, we expect this to be positive. And so when we subtract a negative, it's a positive 2.08. So you get 1.90 volts is our answer. So don't overlook this. Cell potential is not supposed to be hard. In fact, there's quite a few problems on this, on the test that I'm writing right now, that I'm not trying to do. Most of them are going to be actually surprisingly simple. Surprisingly simple. The only problem comes when it's not a galvanic cell and it doesn't tell you it's a galvanic cell, and you assume it's a galvanic cell unless you get it wrong. So if you're given an equation like this one, copper plus silver goes to copper plus 1 and silver solid. Never assume that it's going to be positive. Whenever you're given a chemical equation, you look it up and you do the math. So I'm going to pull this up. This is one of those things. I do not have these numbers memorized. There's one number I have memorized, and that's hydrogen. And that's because hydrogen is conveniently 0. Okay, so depending on what source you have, these may be in either alphabetical order or this one's set up in order of size. So you just have to keep scrolling until you find the one you want. We have, make sure you find the exact equation, but keep in mind, sometimes a product may be hidden if it's like water and it cancels out. If product may be hidden. But so in this case, we have silver goes to silver plus 1. Oh, but silver plus 1 goes to silver, and that is positive 0.8. And then we have to look for copper. So there's copper plus 1. And 1 electron goes to copper solid. And that's 0.52. Now, how do we do this? You go, okay, we have silver as written. The silver as written is the reduced. The copper is reverse as written. It's the opposite as it's written. So it is the oxidized. So I'm going to take the opposite of the copper, which is, and so subtract 0.52 from 8. 0.52 from 8, and so our answer will be what? 0.28 volts. So these are not meant to be hard. These are meant to you understand the basics here. Oh, shoot, I need to. I probably need this for the next one. So, look. Okay, now, however, keep in mind, because of the nature of this, the easier it is to reduce something, the harder it is to oxidize something. Just like a strong base makes a weak conjugate acid, and a strong acid makes a weak conjugate base. A strong oxidizer makes a weak reducer. So looking at that same chart, you can find out, so an oxidizing agent gets reduced. Which of these values are the highest on that table? Is it iodine, bromine, chromium 2 plus, aluminum 3 plus? Which one of these are higher up? And you put them in order of highest to lowest, and that will give you your answer. Okay, which one of these guys will oxidize zinc but not silver? Once again, you have to look at your table. Calcium, bromine. So they have to oxidize zinc, bromine, calcium, cobalt 2 plus. And they're on purposely throwing in some ones that are going to be stupid. Okay, I'll do just half of this because once you see what you need to do, it's self-explanatory. You need to find the if you're trying to oxidize, you're trying to find something that is between the silver and the zinc, between the silver and the zinc. So silver was right here, and you're trying to find the oxidation, the reduction reaction. So you need something that is below silver, but above zinc. So silver being right here, we need some. So looking here, we're looking for cobalt, calcium, and bromine. Cobalt, calcium, and bromine. We have scrolling down. So, oh. There's cobalt 2 plus. Cobalt 2 plus. No. There's zinc. There's zinc. I just want to keep going down. I think what bromine is maybe above. There's calcium well below zinc. And if we scroll all the way up, I'm sure bromine is actually above silver. But going back to here, there's only one. So cobalt, not cobalt neutral, but cobalt 2 plus, because you want a thing that will be reduced. Cobalt solid is not going to go to cobalt negative. Cobalt 2 plus can be reduced, but cobalt 0 wants to be oxidized. So you're trying to find the guy who will be reduced of that pair. Calcium 2 plus wants to be reduced. Bromine elemental wants to be reduced, but bromine 1 minus doesn't want to be reduced. Calcium solid doesn't want to be reduced. Cobalt solid doesn't want to be reduced. So you're finding, just like you have an acid and conjugate base, you have a reductant and conjugate oxidant. And so you want to find the guy who will be reduced. And then you'll have to find which of those guys fits in right between zinc and silver. Same thing here, going down, like which of these reagents would oxidize copper but not fluorine? So it would be between copper and fluorine. So once again, you'd look at, and note it's copper +1, not copper 2 plus. And so you'd look at that table and find that chart. Okay. So potential, okay, this one wants us to do two steps. They want us to find the E non-standard. So our reaction is zinc plus nickel 2 goes reversibly to zinc 2 and nickel. And they're giving us, it's 25 degrees, so 298. And they give us the zinc concentration is 0.804 and nickel is 0.018. And we got to find out the E cell from the table. E cell from the table, well, we were just at zinc. So where's nickel? Unfortunately, nickel is, who knows where nickel is? You just kind of have to scan that. I will give you a chart like this on the test. You just have to scan the chart, try to find the reaction. Nickel is, okay, there's nickel. Nickel is written as negative 0.26 volts. So zinc is the guy who gets oxidized. And so it's going to be minus the zinc. That's negative 0.76. Okay, now I'm going to go to the dot cam. The first thing I am finding is the E cell standard. The E cell standard. So that's our nickel minus our zinc. Nickel minus our zinc gives us 0.50 volts. Now my reaction, my actual equation is E equals E standard plus RT, what is it? I think it's negative RT. Yeah, negative RT over NF ln Q. I'm going to real quick pull. I just want to, let's see. Oh, for God's sake. Wrong way. Because that positive or negative will matter. Negative RT. Yeah. Okay. Negative RT ln Q. And our Q, let's not forget, is products over reactants raised to the power over their coefficients. We don't include solids. We don't include liquids. We only include aqueous and gases. So it's just zinc and nickel. It will not matter the concentration of the zinc solid. So first things first, what is our Q? .804 divided by 0.018. Our Q is 44.6 repeating. So I'm just trying to do this systematically so you can see, oh, where's all these numbers coming from? You're like, oh, okay. So our negative RT, so negative 8.314 times our temperature, 298, over N. So this is the only tricky part. N is the number of electrons transferred. Zinc goes to zinc 2 plus, that's 2 electrons. Nickel goes from 2 to 0, it's 2 electrons. The electrons transferred are 2. It's the greatest common factor between the two. If one is 1 and the other is 2, the greatest common factor is 2. If one transfers 3 electrons, the other transfers 2 electrons, the greatest common factor is 6. And the balanced chemical equation will show the number is 6. And F, Faraday's constant, 96485. You will be given that number, ln 44.67. So, and we're going to add that to, well, subtract that from our E, which is 0.5. So what is the RT ln Q part? 0.314 times 298 divided by 2 divided by 96485 times ln of 44.6. Repeating. In this particular case, it's going to be minus, say, 0.0, we'll say 5. It's 0.0487. But the E cell then becomes 0.45. The voltage has dropped by a fractional amount. Not a huge amount, but enough of an amount that had I just plugged the number in into this, it probably would mark it wrong.
So the ordering going through that, like, did you put the calculator in the right order?
Yeah.
The RT over NF, that's all done together.
Yeah. Yeah, RT over NF ln Q, all that's done together. Yeah. So basically what I have to do is I could do this all in parentheses. Go back to the doc cam real quick. So, and it's like, so I have to make sure all this is in parentheses and all this is done ln Q. So that negative sign makes that a negative 0.05. If I did this, this is a positive number. ln 44 is a positive number. So minusing that becomes minus 0.05. When you punch this into your calculator, you can punch it into one of two ways. You can say R times your T divided by 2, or divided by your N, divided by your F, times ln RQ. Or you could do it R times T divided by, in parentheses, N times F times ln Q. But you got to make sure you get the N and the F both on the, all of that. Yeah, all of that. So this whole thing, that whole thing right there by itself, without the lnq, is actually 0.0128 something. It's a really, really small number. And it should be a really, really small number. Unless the temperature is really high, in which that would increase it. But really, the large change comes from our Q. That's where the change can best be dealt with. Okay. Oh, sure. Let's see what other problems we got. Okay. Voltage generated by, okay, so this is a electrolytic cell. This is a perfect example of that in action. So that same equation, you have the voltage, the E non-standard is 22 millivolts. 22 millivolts. So that means that is 0.022 volts. And they want to know, what is the concentration of zinc at the cathode? 0.100. So you got zinc 2 plus, and you have zinc 2 plus. Now, it's at 25C. 25C. Okay. Now, the problem here is when in a situation like this, zinc goes to zinc 2 plus, zinc 2 plus goes to zinc, this is negative 76. This is negative 76. Left to right, right to left, they cancel out. E standard is going to be 0 volts because the both half reactions are the same. So the whole equation, E equals E naught minus RT over NF ln Q. Well, this whole part goes to 0, so the voltage is only controlled by the concentration. This is a concentration cell. So our Q is going to be products 0.1 over reactants, which is our X, our unknown value. We know R, we know T, we know F. What is our N? Our N is we go from 0 to 2. So with this being 0.022, that's equal to negative 8.314 times 298 over 296,485 ln 0.1 over X. Well, let's say variable. I mean, I'm trying to make sure these are multiplications and that's actually a variable. So what do we have to do? Step by step, get those to the other side. Get those to the other side. This is why we ask you to be in pre-calc. We want you to be able to do, okay, 0.022. 0.022 times our 2 times our 96485 divided by 8.314 divided by 298 and make it negative. So right now I got negative 1.7135 equals ln 0.1 over x. How do we get rid of the ln? This is where our kinetics comes in. This is where all the stuff we've been working on comes in. We do the inverse natural log of both sides. Inverse natural log will take care of that ln. We're going to have this, it's second ln to get the e power and plug in our answer. And so you get 0.1802 equals 0.1 over x. So the last step is to get x over here and over there. So you're going to have x equals 0.1 over 0.1802. Second answer, you would get x would be 0.554. Wait, 554. Now let's go back to achieve. Try that number in. Okay. I'm doing this one because this one is actually a little bit of a challenge. I'm not going to say this is easy. Well, this is application of something that we'll use 1 or 2 times, but it puts everything into context. All the suffering with our Ks and our Qs, and it brings it into focus as we're trying to turn E cell into what concentration zinc has to be to create that voltage. Now, this one is just thinking about this. If E cell is positive, delta G is negative. If delta G is negative, the reaction is spontaneous. The reaction is spontaneous. Is it product favored or reactant favored? And say, well, if it's spontaneous, it's product favored. If it's product favored, that means you'd have a large K. So saying you have a negative standard free energy, so E is positive, so you'd have to answer that question. Which of these statements would hold true if delta G was negative? So, same thing here. If Q is greater than, if Q over K is less than 1. If Q over K is less than 1, that means that Q is smaller than K. What does that mean? Q is smaller than K. It means we are not at equilibrium. It needs to increase the number of products. It's too far to the left. So what would that mean? Is it spontaneous? Yes or no? And so you're answering those relative questions. So that's a head puzzler. See, this one, okay, I'm looking at the last couple ones real quick. Okay, we'll do the 18 and 19, and that'll be where we'll stop, because 20 is just another one of 19. This one asks you to do delta G using the cell potential. Now, on a test, if you are given the if you're not given the delta G values, you're not given the delta G or delta H or delta S values, and you're asking to find delta G, you have to use the voltages. So I'm writing down my equation. It's done at 25. So the idea here is that delta G equals negative NFE cell. Delta G standard equals negative NFE. So if I have N and I have F and E. If I can find E cell, I can find our delta G. I need zinc. Zinc is right there, 0.76. Gold. Gold's going to be up a bit. Oh, there it is. 1.498. Took me forever. But, okay. Now, I got the values I need. Got the values I need. .cam. So, we do the reduced minus the oxidized. So I'm subtracting the negative. We're going to get a big number, 1.498 minus a negative 76, negative 0.76. You get E cell is equal to 2.258 volts. Now, here's the only hard part here. 3 electrons are gained by gold. 2 electrons are lost by zinc. The greatest common factor between 3 and 2 is 6. N is going to be 6. Because you got to remember, gold is losing 3 electrons 2 times. Or it's gaining 3 electrons 2 times. Zinc is losing 2 electrons 3 times. The number isn't 12, but the number isn't 3, the number isn't 2, the number is 6. So our answer would be 6 times 96485 times 2.258. And then we got to divide by 1,000 because of kilojoules. Kilojoules. Negative. We want kilojoules, not joules. Otherwise, this would be an incredibly large number. It probably is still going to be an incredibly large number. Even having divided by 1,000, it's still 1,307. So the idea that if I put zinc solid next to a gold solution, wham, like a ton of bricks, it's going to be, it's very spontaneous. Very, very spontaneous. It's going to happen. Okay. Last question we'll do is a voltage problem. The current of 4.86 amps, 4.86 amps is passed through copper nitrate. So this is copper 2 plus. How long in hours was the current be applied to plate 7.6 grams of copper? 6. So the equation is mass equals current times time times molar mass over NF. I'll give you this equation on the chart, on the test, but it's so we're looking for time. The mass, 7.6 grams, equals 4.86 times our unknown T, times what is the molar mass of copper? Copper is what, I'd like to say 63 something. 63.5 maybe. 63.5. Oh, yeah. N, because we're going from copper 2 plus, it's 2. 96485. And how do I know it's copper 2 plus? Because it's copper nitrate with 2 nitrates. Copper. We don't have to include the nitrate in the mass because we're not depositing the nitrate. But the nitrate will tell us how many coppers. What's the charge on copper? So 7.6 times 96485 times 2. That gets that to the other side. Divided by 63.5, divided by our current. Gets the time. The time right now is 4752 seconds. It's always going to be seconds because current is coulombs per second. That's what an amp stands for. Now, because it asks for hours, we turn it into minutes, and then we turn it into hours. So to get 7.6 grams of copper, it would take 1.3 hours. And that is, as I said, this is at least most of the problems on the last major assessment. Now, as I said, the last one is another one just like this. I'm not going to do this. They give it current. It's nickel 2 plus. They give you a time in hours, and they want you to find the mass. Once again, the only problem here is you have to turn hours into seconds. Otherwise, it won't work. Because current assumes seconds. Current, it's like saying miles per hour. Miles per hour assumes hours. If I say I travel for so many days at this speed in miles per hour, you can't just take days times your speed. You would have to turn the days into hours. Okay, but that is that. Leave that for you guys to figure out the rest. In the meantime, we'll start briefly chapter 20, nuclear chemistry. Oh, I gotta pull that up. So, now, unlike with chemical reactions, a nuclear reaction will deal chiefly with the nucleus. And so all parts of the nucleus, the protons and the neutrons, are together usually referred to as the nucleons. But for this chapter, we'll have to recall atomic number, which is our number of protons, atomic mass, or the mass number, which is the protons and the neutrons, and the concept of an isotope, elements with the same atomic number but different mass number. Now, the proton and neutron account make up a big part of what makes a stable nucleus. The idea here is that too many of either protons or neutrons will make the nucleus unstable, just like there's only certain amounts of electrons that can be held in the outer shell. If I try to take 3 electrons from calcium, you're going to have a problem. Same way as if I try to give 3 electrons to oxygen, you're going to have a problem. Oxygen is at 6. It needs 2 to make 8. 1 more, 1 too many. But an unstable nuclei will break apart and start radiating particles until it's stable again. Just like if I gave calcium, if I gave oxygen 1 too many electron, it's probably going to shoot that electron back off. But the basic idea here is radioactive decay results in a nuclear change that will change the elemental structure through a process called transmutation. This is the only way one element becomes another. Alchemists were busy trying to turn lead into gold, and they could have done it had they had an atom smasher and unlimited money. All they were doing was changing the chemical formulas of lead, making different lead oxides or chlorides or all the things, but it was still lead in itself. But this way, you literally could turn lead into gold. You hit lead, you subtract 3 protons and enough neutrons from lead, you will make elemental gold. Now, some Elements are radioactive, some are stable, and some are always radioactive. Some are always radioactive no matter what you do. Some just have certain isotopes that are radioactive. So like cobalt, usually pretty stable, but we can generate a radioactive isotope of cobalt that's used in medicine. Same thing with iodine. Iodine usually pretty stable. It's taken up by the thyroid, among other places, and by making the radioisotope of iodine, you can help fight thyroid cancer because you allow it to be absorbed chiefly into the thyroid, and then it shoots its ionizing radiation directly into the tumor that happens to be there. Now, we may have heard of the first three types of radiation before, if we were paying attention in Gen Chem 1, but we're going to introduce one or two more. So alpha particles, abbreviated by the Greek letter A, the alpha, is essentially the same as a helium nucleus. 2 protons, 2 neutrons. It's the heaviest type of radiation that can be formed by most, if not all, elements, shooting off a stable 2 and 2. There's beta decay. Now, beta decay, it's essentially a high energy electron. It has a negative, it's like, it has essentially no mass, or essentially electron's mass, and essentially be like a -1. Now, gamma is just pure energy. No mass, no loss of protons. It just helps calm some things down. Some things will shoot off gamma radiation in addition to other types of decay, but gamma will not change an element. So a new thing is a positron. If a beta was like an electron, the positron, which is beta plus, is like a positive electron. It's not a proton, because unlike a proton, it has almost no mass. Proton would be like 1 charge, 1 proton. If you put in the atomic number, it'd be 1/1. Well, a positron would be 0/1. It'd be like losing no mass, but losing the part of a proton. Now, electron capture is not really a decay type, but its electron is absorbed from the electron cloud into the nucleus. And so rather a particle loss, electron gets sucked into it, and it's a different way of which a transmutation can happen. But all of these incidents will involve a parent, which undergo one or more types of decay, releasing what we call a daughter nuclide. Parent produces several daughters. Now, here's some examples. Here's a reiteration. So alpha, so radium undergoes decay. It's 226 and 88, and it loses an alpha particle. This alpha particle, it's like losing 2 protons, 2 neutrons. So 88 goes to 86, and 226, because it lost 4 mass numbers, goes to 222. So radium undergoes alpha decay to form radon. This is how radon gas seeps into our basements, that there is deposits of radium. Well, radium comes from like uranium and whatnot, but like there's deposits of uranium deep within the earth. It decays to radium, which decays to radon. Now, a gas being lighter than dirt is going to find cracks in the earth and seep its way up to the highest area. And if it happens to be below your basement, it can easily get trapped in your basement and thus fill your basement with a colorless, odorless, ionizing gas that can be deadly. And so they often ask people with homes, with basements, to get a radon detector, and there's possible ways to vent it to the atmosphere to safely get it out. Beta, which is like 0, -1 electron. Beta, neutron. So here's an interesting thing. So when a beta decay happens, a neutron breaks apart into a proton and a beta. A neutron has one mass number and it's 0 charge. So we're breaking apart that neutron into basically a positive half and a negative half. The positive half gets the charge. The negative half, the positive half gets the mass. The negative half gets nothing. And so iodine 131 undergoes beta decay to form xenon 131. Beta decay, the mass number stays the same, but you'll notice this is changed from 53 to 54. So 54 plus a -1 equals 53. The mass number additions add up. Gamma decay, excess energy is released as the electron relaxes. So cobalt 6027 undergoes beta decay to nickel, which is then high, and some gamma. And then the nickel, which is highly charged, also undergoes more gamma to relax. So the nickel in here stays the same. It's just high energy nickel to lower energy nickel. Now, a positron is the exact opposite of a beta. Instead of a neutron breaking apart, a proton breaks apart to form a neutron and a positron. So a proton, which is mass 1, charge 1, kicks off the charge component and becomes a neutral proton. It kicks off the charge component, becomes a neutral proton. So in this case, carbon 11 kicks off the positron, become boron 11. You notice that the mass number is still 11, but 6 equals 1 plus 5. Positron emission moves it to the left. Beta emission moves it to the right. Alpha moves it 2 to the left. Electron capture also moves it to the left. Electron capture, orbital electron is captured by a nucleus, combines with a proton to make a neutron. So a proton's 1 and 1 gains a 0 and a -1 to become a 1 and neutral. So rubidium 51 absorbs an electron to become krypton. Sorry, not 51, 81. Become krypton 81. Now, positron and electron capture, they essentially do the same thing, but one is for light elements and one is for heavy elements. But you don't actually have to understand how it happens. You just have to be able to do this math right here. But it's, some people wonder what the hell's actually going on, and so I'm trying to actually provide. This is what literally happens. A neutron shatters apart into a proton and the beta particle. The beta gets kicked out, and the proton is just shifted around in the nucleus to make it stable. So predict the products of these decays. You'll have to be able to do this on the test. Not too hard, but you have to be able to look at a periodic table and figure this out. Sodium equals beta and what? Let's see. Boron 8 yields positron and what? Let's see. Iodine 125 plus the electron capture gives you what? Francium 211 undergoes alpha decay for 2 alpha and what? Okay. As I said, you look up on the molecular formula, you look up the periodic table, you need to know the mass number and the charge number. The mass number. Mass number will always be given. There's no way you can figure that out otherwise, because we're not using much like when we dealt with atoms before, we're not using the average atomic mass. We're using the specific isotopic mass. So sodium. So whatever our product is, 24, is not going to change, because when we do this decay, 0 plus 24 equals 24. We're going to treat this arrow as an equal sign. The left and the right have to be the same. Now, sodium is what, like 11. Beta decay is going to move it 1 to the right, because this has to be 12. Now, the element that is under element 12 is magnesium. 12 plus -1 equals 11. 12 plus -1 equals 11. Now, boron undergoes positron emission. So this 8 doesn't change, because 8 plus 0 is still 8. However, this has to go to 4, because 4 plus 1 equals 5. So positron shifts it 1 to the left. So 1 to the left of boron is beryllium. We cannot figure out the element till we figure out the atomic number, but the atomic number makes the element. Iodine. Oh God, what is iodine? Iodine is, sheesh. I mean, I could probably, well, I'll trust you on that one. We'll go with that, 53. 125, when it undergoes electron capture, the mass does not change. So it's still 125. But 53 plus -1 brings us to 52. Either way, electron capture moves it 1 to the left, which is tellurium. And the last one, francium. Oh, francium, right there by radon. No, radium. No, radon. 87, yeah. Francium, 87. This drops the mass by 4. So 211 becomes 207. And drops the proton count by 2. 85. Either way, francium goes to astatine. As it moves it 2 elements to the left. 2 elements to the left. 85 plus 2 is 87. 207 plus 4 is 211. If you can do that, you're looking at 2 easy questions on the test. I'm telling you right now, I'm not going to do a lot from this chapter, but this is one of those things we will be doing. So I'm going to look through this real quick. Beryllium, tellurium. So, now, we'll look at this. We'll finish after this slide. But naturally, radioactive elements rarely undergo just one decay. We'll actually undergo a series of decays in what's called a radioactive series. We'll undergo a lot of alpha and beta, sometimes some gamma decays to get a stable nuclide. Now, when we're measuring these, measuring these in disintegrations, essentially particle emissions, given as per sec as an activity. Disintegrations per second as the activity of it. We could use this as Becquerel, or disintegrations per second, or a Curie as 3.7 times 10 to the 10th Becquerels. The Curie is specifically the measurement of the activity of radium, which is one of the elements that Curie helped discover. But so like uranium, you'll see here, uranium starts up here and undergoes alpha decay down here. 2 beta decays to get up here. Then it's alpha, 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 alpha. series of alpha decays. And then it can either go beta, then alpha, and then beta, 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 alpha, or beta, beta, alpha, beta, beta, alpha. Either way, uranium undergoes a series of decays to eventually get down to lead down here. Lead, can't really read the mass of lead, but uranium will eventually decay down to lead. It takes thousands of years, but what, millions and billions of years. But it is a very standard thing. Uranium is naturally radioactive in all isotopic forms. It just, thankfully, it's a slow process. Now, this detector, how they work. Essentially, you have some like gas atoms in here within this window, and it's like a little nozzle. As the ionizing particle gets into there, it's going to hit the gases, knocking off electrons, creating a charge that can be picked up on the electronic detector down here. And it's going to measure how many particles are being generated, essentially, how many ions are being formed when it collects these ionizing radiation. It shoots into there, and like beta decays are the negative electrons, hits those particles, charges the gases stick to the positive charge, help pick up the electric circuit, and you can say, oh, there's a bunch of ionizing radiation shooting at us, or not. Now, there was an interesting story a couple years, 5-10 years back, about a museum in like, I like to say Arizona or New Mexico, that had like some like paint just sitting there, like, and like it turns out there was radioactive paint left over from like the nuclear tests back in the Manhattan Project, and like it took a boy who loved radiation detectors to like figure it out. They're like, oh, what's the beep 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 beep? Whoa, it's like they were just thrown in the back of someone's truck and dropped off there, and it was a very interesting story. Just like don't take things for granted. But okay, we will stop there. This will not be a long chapter. We'll go through kinetics. We will go briefly into calculating the energy of nuclear reactions, but that will not be on the test. We'll go briefly into what makes a nuclear reactor tick, what makes a nuclear bomb tick, for that matter. But not all that stuff will be on the test. But that transmutation thing we just showed you, that will be, expect that. Either way, thank you for your time, and I will see you, well, see you in lab and see you whenever.